Welcome back. In this video, I will talk about how do we use the drop weight method to measure the surface tension of solutions and determine the absorption isotherms of solutions. The drop weight method for measuring surface tension is accurate and one of the most convenient methods for measuring surface tension in the laboratory. It is quite literal, where we put solutions through a nozzle where we look at the solution dropwise, measure the weight or volume of each drop to determine the surface tension of the solution. And almost 160 years ago, Tate proposed a simple model where it's assumed that the gravitational force or weight of the droplet is balanced out by the surface tension force. That is, the sigma times the perimeter of the nozzle, which is 2 pi r, is balanced out exactly. And sigma is the surface tension and r is the nozzle radius. And the nozzle radius is dependent on whether the drop is forming out the exactly outer edge of the nozzle, or if the drop is forming on the inner nozzle, then the r will be smaller. Because they're balanced out, Tate derived the equation where W, the weight, is equal to 2 pi r, the perimeter, multiplied by the surface tension. However, this is a big simplification because there are when the droplet is forming, there are some intermediate droplets or satellite drops goes in between, and there are some leftover drops at the top. So in order to correct for this, Harkins and Brown in 1919, which is almost 100 years ago, proposed that we can modify this using a correction factor by multiplying a small f. Or to write it out more eloquently, we can define a big F which lumps all the constants together, and we can get in the form of R times the surface tension sigma divided by big F. This correction factor, which is usually a function of R and B, which is the volume of the droplet and the radius of the nozzle. And in 1971, a correlation for the correction factor was proposed, where we have this whole equation. If we know R and V, then we can know the correction factor. And usually the R divided by V to the 1/3 is within the range of 0.3 to 1.2. Remember that the drop weight method is for determining the surface tension of solutions. So we want to solve for sigma. So if we go from Harkins and Brown's equation, we can solve for sigma, where we have sigma is equal to the weight multiplied by the correction factor F divided by R. And the weight of the droplet, you should think about it again. What is the actual weight of the droplet? The weight of the droplet is the gravitational force of the droplet, but it is also counterbalanced by a buoyancy force. And in this case, we have the outer medium is air, and the solution is the droplet. The buoyancy of the air usually can be negligible. However, if we write it out, the buoyancy force would be the rho times rho, which is the density of the air. Let's say air is the phase 2, times V, which is the displaced volume of the droplet within the air, times G. And the gravitational force of the drop, which is just mg, which is the m can be written as rho V. And rho, we say it's phase 1, and then multiplied by G. So the net force is the difference in density of the solutions multiplied by V. We are only concerned of the absolute difference. So this is the net force. So we can plug this in. Sigma is equal to the difference between density of two different media multiplied by V G divided by R. And that's how we calculate the surface tension. Notably, if we have significant difference in the density of the solutions, for example, if we have water within air, then one of the density would drop out to almost zero, so that we can have V times rho, and let rho 2 defined as rho times G F divided by R. And note that the mass is just rho times V, so we have mass times gravitational acceleration times correction factor divided by R. So in the simple case of a big difference between density, we have the surface tension is just weight of the droplet multiplied by correction factor divided by R. However, we must note that F is a function of R and V to the 1/3, so we actually need the volume of the droplet. So since we cannot directly measure the volume, then we need density of the droplet. Therefore, to determine the surface tension, we'll need the rho. We need to measure the droplet's density, rho, and the volume of each droplet, which can be replaced by mass. Because once we know mass and the density, we can know the volume. We should also know the nozzle radius, and we can know or assume the gravitational acceleration. After knowing how to calculate the surface tension from the drop weight method, then we can look into surface tension of solutions and see how they change with respect to concentrations. For example, the Szyskowski equation describes the surface tension of a binary aqueous solution, and it correlates the surface tension sigma with M2, and where M is the molality, which is one expression of concentration in terms of mass, in terms of mole per of solute. The Szyskowski equation, sigma is surface tension, and sigma 0 is surface tension of pure solvent. And for example, if we have aqueous solution, then sigma 0 is the surface tension of water. R is the ideal gas constant. Usually in the SI unit, R equals 8.314 joules per mole. And T, of course, is absolute temperature. Always use absolute temperature. And A and B are empirical constant that we want to fit. And then M is the molality. And we graph the Szyskowski equation, where we have on the x-axis we have the molality of the solute. On the y-axis we have the surface tension. Then we'll see a trend like this. where we see at lower concentration, this range, we see a big drop in the surface tension. However, as we see that the solute concentration increases, change in the surface tension is less and less. Using the Szyskowski equation, we can relate the surface tension of a solution to the solute concentration, or a binary aqueous solution. If we have a binary solution of alcohol, for example, we have an alcohol aqueous solution. Imagine we have an alcohol that has a hydrophobic region. It's just a carbon chain, and the hydrophilic region. The hydrophilic region is the OH group, where it can form hydrogen bond with H2O. So that, if, for example, if we have a droplet of water, of our alcohol aqueous solution, and the outside is air, then the hydrophilic portion of OH group will be preferentially located within the solution, so it can interact with water. Outside of it is the hydrophobic region that interacts with the air. And when the adsorption of the alcohol to the interface between the solution and air is established at an isothermal condition, then we can use the Gibbs adsorption equation for an ideal solution, which describes the relative absorption denoted by big gamma 2 to 1. Is the 2 is the solute, and 1 is the solvent. So in this case, the relative absorption of alcohol to water with respect to water is equal to the negative x2, which is the mole fraction of the solute. And in this case, the mole fraction of alcohol within water. And R is the ideal gas constant, T is the absolute temperature, sigma is the surface tension. For ideal solution, Gibbs absorption equation tells us that the relative absorption of solute with respect to solvent is equal to the negative of the mole fraction of solute divided by RT multiplied by change in surface tension with respect to the change in mole fraction of solute. When it is an ideal dilute solution, then we can say that the molality, which is a concentration, again, which is mole divided by kilograms, mole per mass basis concentration, and replace the mole fraction. When the system is not ideal, then we need to make corrections based on the activity coefficient based on Henry's law. Here, gamma is activity coefficient based on Henry's law. And note that this term, if the activity coefficient is not a function of the molality, then the entire derivative will go to 0. And if it goes to 0, it just falls back to the ideal case. So it verifies that this equation, when the relative absorption gamma 2 of 1, which is solute with respect to solvent, is greater than 0, positive, then we can say that the interfacial layer is enriched of component 2 compared to the bulk phase. So if the bulk phase has relatively few alcohol, but the interfacial layer has more alcohol, we say that gamma 2, 1 greater than 0. We say component 2 is positively adsorbed with respect to component 1. In this case, alcohol is positively absorbed with respect to water. And in this laboratory, we want to look at how the relative absorption is dependent on the concentration. That is, we want to use Gibbs absorption equation to see how gamma 2, 1 is a function concentration in terms of molality. After knowing the background equations for this experiment, we can go into each objective and look at how can we perform this experiment. First of all, the experimental setup, we have a syringe pump that is connected to a syringe. And in the syringe, we fill with a solution of interest that we want to determine of its surface tension. At the top, we have a tip where we have a nozzle here that is very delicate. Please do not damage the nozzle. Do not use nozzles that have chips or any fouling on it, because it will affect the surface tension measurement. So we want a flat nozzle at the top, and we want to make the solution come out of the nozzle dropwise. That's why we want to have a drop weight. And we want to place a weighing flask under the nozzle. First, we weigh the empty flask from 0. Then we also want to weigh flask filled with drops of water. And the difference between them will be the weight each drop. However, because measuring each drop has such a small mass, we would want to fill around 10 drops and measure the mass difference and divide it by 10 to get individual drops mass. Again, to determine the surface tension of water and aqueous solution, we will use, on the ambient condition of other phase of air, we can neglect the buoyancy force of air and use the surface tension is directly related to the weight of the each drop divided by the nozzle radius r multiplied by a correction factor that is a function of r and v, which is the radius of the nozzle and the volume of each drop. And to know the volume of each drop, we know m, so we want to measure the mass of each drop. And how do we get volume? We want to calculate volume. To calculate volume, we also want to measure the density rho of each of the droplet solution, so that we can get V equals to, so rho equals to m divided by V. So V equals to m divided by rho. And then we can calculate the correction factor using R and V. R, let's say R is known because it will be given to you on the lab manual. And then we know the and then we calculate F. We know F, we know R, we know M, and G is also a known, so we can calculate sigma. And sigma is the surface tension goal that we are achieving. So this is the part that we measure the surface tension of any solution using the drop weight method. After knowing how to determine the surface tension of the solution, then we can extend it to different types of solution. For example, we can look at solutions with various concentrations. And for solution of different concentrations, we can fit the curve to see that sigma with respect to the molality behaves according to this equation, the Szyskowski equation. And in this lab, we want to use data points to fit this curve using nonlinear regressions in order to determine the Szyskowski parameters A and B and other things we can measure. So R is a known. So we know R, and we want to measure the temperature, ambient temperature of the room, and the surface tension of water, which we can measure using this procedure. Just measure sigma, and including sigma 0, which is just the water surface tension. And M we also know because we have prepared the solutions. And then we can finally calculate sigma, and which is function of the molality. The second part of the experiment wants you to construct an adsorption isotherm. And what is an adsorption isotherm? So it is when the experiment is kept at isothermal conditions, where there is no temperature change, delta T equals to 0. And we want to see the relative absorption, so beta gamma of N-butanol is 2 with respect to water 1 at the air-water interface versus the concentration in molality of the N-butanol. So we're expecting a graph that looks like this. On the y-axis, we have the relative absorption, and on the x-axis, we are plotting 2, which is the molality of butanol. And we would expect something like this. At lower concentrations, the increase in relative absorption is relatively fast. However, when the concentration increases, the increase in relative absorption decreases. So it's not increasing as much. For an ideal dilute solution, we can use the ideal Gibbs adsorption equation here. However, for a more general case, we would use the activity coefficient to correct for non-ideality. In this case, let's identify what we are measuring, what we're knowing, and what are we calculating. First off, we're definitely calculating for the relative absorption of butanol at the air-water interface. And M2 is the known concentration in molality of the N-butanol in the aqueous solution. We also know the ideal gas constant R. We want to measure the absolute temperature in the room, which will be equal to the temperature within the droplet. And then this term of the d sigma with respect to dm2, then we can, how do we get that? Measure that using a table where we already have measured the concentration and the surface tension. For example, I have 1, 2, 3, and I also have some number, for example, 1, 2, 3. Then we can get the slope between the data points. For example, if I want to know this point, then I can use sigma 2 minus sigma 1 divided by m22 minus m21 to determine the slope at that point. So that's how we get d sigma divided by dm2. And similarly, for the non-ideal case, we're just dealing with one more factor of non-ideal correction. And that non-ideal correction can also be determined from a table where we show in here. We have the molality and the activity coefficient of n-butanol water. Because in this case, we're taking the derivative of the natural log of them. So in Excel, you would do is to determine the natural log of M2, and another column, the natural log of the activity coefficient, Henry's law. And to determine the slope at one particular point, for example, I want to determine molality 0.01 molar, then I'll take these two data points, these two columns. So we have the activity coefficient, the natural log of activity coefficient. But we are actually taking the natural log, so these 4 data points, say A, B, C, D. We're taking the derivative, then it is D minus B divided by C minus A. So we're finding the slope. That is the slope at this point. M2 0.01. And we want to do that operation at each point of M2 so that we can have enough data to actually generate this plot, fit the data point. So we're looking for 2 plots. One plot is the ideal dilute equation, and another one we're looking for is the general case. And that is fitted from 2 different set of data. For example, one is solid dots and one is hollow dots. And we want to fit 2 nonlinear equations through them. One through the ideal dilute and one through the general equation. Other small objective of this experiment, we can explore the surface tension of water with respect to the nozzle size. So we're plotting the surface tension of water with respect to the nozzle size r, or the radius. So think about how would the surface tension relate to the nozzle size, the method of measurement. We know that surface tension is a thermodynamic property, so it shouldn't change with respect to how we measure them. But in reality, in practice, how could this differ? And the second objective, we have surface tension of water versus drop formation time t. So if we wait longer, so allows it to establish equilibrium better, how does it change surface tension measurement? We have to know that it is the apparent value of surface tension of water. So the surface tension measurement value is not the actual surface tension, because as a thermodynamic property, the actual surface tension does not dependent on the measurement method. Let's write that down. So the actual surface tension and the apparent surface tension. The actual surface tension is the thermodynamic property and does not depend on measurement method. So this is like the ground truth. And the apparent surface tension is what we measured. So it does depend on measurement method. In this case, we're exploring how the apparent surface tension will depend on the nozzle size. So let's just write nozzle size R and the drop formation time T. We have to keep in mind that these are different. And we want to compare how the apparent surface tension changes and compare them to the ground truth actual surface tension tabulated. And again, we also want to explore the surface tension of a surfactant solution of Triton X100 and how it changes with respect to drop formation. And finally, we want to compare the surface tension measurement of water with other groups who did a drop weight, the ring method, the slide method, as well as sessile drop or pendant drop.